Okay, let's talk about MOSFETs. Okay. So we introduced MOSFETs in last class. Let's see. Okay, there we go. So this here is a N-channel MOSFET. And we start off with a P-type substrate to create an N-channel MOSFET. And vice versa. If you want a P-channel MOSFET, we start with an N-type substrate or an N-type wafer. Right now, we're going to focus on the center right here. Right, MOSFET stands for metal oxide semiconductor. Metal oxide semiconductor. And so this creates a sandwich layer right where the gate is. What structure does this create? It's two conductors separated by an insulating material. It's a capacitor. So this is known as the MOS capacitor. And for the next slide, we'll see how this MOS capacitor operates. Okay. Now, the key thing or the key difference between the MOSFET and the JFET is that the JFET is a depletion mode device. Okay. When you manufacture a JFET, the channel is already present. Okay, the channel is already present. So we have two terminals. We have current flow between the two terminals, and we use a third terminal called the gate to control the flow of this current. Right. So in the JFET, the channel between the two terminals is always present. We must apply an external voltage to turn the channel off. Hence, we say external voltage must be applied to turn the device off. In this kind of MOSFET, channel is not present. The channel must be created by the application of external voltage. And so in this slide here, we see the three regions of operation of how the channel is created right underneath that gate. Okay. So we have the sandwich layer, metal, the oxide, and the semiconductor. The semiconductor is the P-type material right here. Oxide is silicon dioxide, SiO2, and the gate is constructed out of metal. Nowadays, it's not even metal, it's mostly polysilicon. Okay, polysilicon. And polysilicon is basically the polycrystalline form of the silicon material. If you think back, recall chapters 1 and 2, where we talked about single crystal material, polycrystalline, and amorphous. Amorphous does not have any ordered structure. Crystalline material or single crystal material has ordered structure that is repeated throughout the entire wafer or the entire lattice structure, right? Repeated ordered segments. In a polycrystalline material, there are segments that are ordered, but there's no long-term single crystal structure. So polysilicon is the polycrystalline form of silicon material. And that is what is used to create this gate in modern MOSFET devices. It's very heavily doped. So it's heavily doped polysilicon. So it behaves as close to a conductor as possible. Okay. All right. So there are three regions of operation. There's accumulation, there's depletion, and then there's inversion. Okay. Again, the goal always is to use the gate to control the flow of current between the drain and the source, right? You have the drain and you have the source, you have the source and the drain, no matter how, device is kind of symmetrical. And then you have a third terminal, the gate, that controls the flow between the two terminals. Okay. But a channel must be created first. So let's look at the first step, accumulation. So this is a N-channel MOSFET, meaning there are two N-type regions on either side, not either side, embedded inside the P-type substrate. So there must be a channel that connects both the N-type materials, basically the source and the drain. The channel must be N-type. Okay. Again, P-type substrate, N-type source and drain. So the channel that connects the two must be N-type. Okay. So in this gate right now, we first apply a negative voltage. When you apply a negative voltage, what happens? Negative charges attract the positively charged holes in the P-type material. The positively charged holes gravitate towards the negatively charged gate. It accumulates in a thin, shallow region right here, right underneath the surface. So this thin, shallow region is the accumulation of charges. Hence, the state or the region of operation is stated as accumulation. We are accumulating charge carriers. But these are positive charge carriers. So it's a positive channel between the N-type materials. So not as useful. Okay, not as useful. Now, obviously, the charge carriers cannot go through the oxide. The oxide is what is separating the gate from the channel. Now, as the gate voltage is increased in value, meaning going from negative towards positive value, at some point, so here the gate voltage is negative. Here it is increasing in value. And when it increases in value, we're now applying positive charges at the gate. What happens? Positive charges at the gate. So the positive holes are repelled. Positive charges are repelled. You all with me so far? Okay. So the positive charges that were first attracted towards the gate are now repelled into the material. But where did these positive charges come from? From the ionized acceptor atoms. Column 3 elements. Column 3 elements have one less electron, right? They only have 3 electrons in the outermost orbit. So they accept an electron from the silicon substrate to create a P-type material. So if the positive charges near the surface are repelled, what is left behind? The immobile ionized atoms. The ionized atoms now have an extra negative charge, but they cannot move. They are fixed within the lattice. Okay, holes and electrons are free to move about. And when they move, we say charge is being transferred. We say current is flowing through a structure. But these charges here are immobile. They come from the immobile acceptor atoms. Okay, in the P-type material, we are pushing the holes away from the region. So now a region of negative charge exists, but those negative charges are not free to conduct. Okay, that's a big difference. This is a point of confusion for several students. This was also a point of confusion for me when I was a student. Okay, it creates a region that is depleted of mobile charge carriers. It is negatively charged, but it's not due to electrons. It's due to the immobile acceptor atoms. Okay, immobile acceptor ions, to be more accurate. And hence, it creates a depletion region that is depleted of charge carriers. And thus, we call this region of operation as depletion region of operation. Okay. It's not the same cause that we have in a P and N junction, but the result is the same. It is depleted of free charge carriers. So there is no channel that exists at that surface. All right, let's take a pause. Let me know if you have any questions. Yep. Yes. Hmm. Yeah. But it's not free to move about because it's now covalently bonded with the silicon structure. So you had 3 electrons. The 4th electron comes from the silicon structure, which leaves a positively charged hole that is free to move about. But that electron is now bonded with each of the 4 neighboring silicon atoms. Yeah. So you have an extra negative charge because the positive charge is pushed away into the surface. But the negative charges are not free to move out. They are not free electrons. Right? Other questions? Okay. So now comes inversion. The reason it's called inversion is because in the accumulation, we had a positively charged region due to a negative voltage applied at the gate. But now if we increase the voltage to a positive level, after a certain point, depending of course on the manufacturing of the transistor, after a certain voltage is applied where it crosses over a certain threshold, and the positively charged region inverts and creates a negatively charged region. And the reason that happens is because you have positive charges here at the gate, which attracts free electrons to come up from the structure and sit right under the surface of the oxide. Okay, so negatively charged electrons come up, attracted, and then right here, they form a thin, shallow region. Actually, let me wipe this out and do this. They form a thin, shallow region. So now that thin, shallow region that was positive at the beginning, when the device was off, is now inverted into a negatively charged channel. And thus now we have created a pathway of conduction between our drain and the source. Okay. So again, a transistor is 2 terminals. You have current flow between 2 terminals, and you use a 3rd terminal to control the flow of current between those 2 terminals. That's known as the gate. In a JFET, it's a depletion mode device. The operation is different. In a MOSFET, we use the gate to control it by applying a negative voltage. It turns the device off because there is no conducting pathway between the 2 terminals. Then as the gate voltage is increased to positive levels, a channel of N electrons is created between the 2 N-type materials. And now, if we apply a voltage between the drain and the source, those electrons in the channel can drift or move in response to that applied electric field. Okay, so this thin, shallow region is now used for conduction. So we have 3 regions of operation: accumulation, depletion, and inversion. The voltage at which point the inverted channel is established is known as the threshold voltage, VTN. VTN. And this depends on the manufacturer. Some books, it's also referred to as VTO. VTO, threshold voltage. Okay, so VTN is the threshold voltage that is required to invert the channel and establish a conduction pathway between the 2 regions. So this is basically the operation of the MOS capacitor. In the next slide, we'll see how we can actually control it. All right, any questions? Yes. Right now, there is no current flow. This is just the central region where we are establishing a channel so that a conduction pathway is present between the two terminals. That's all we are doing. So this basically is to show how the gate voltage can be used to control the flow of current. Again, the key thing in all kinds of transistors, whether it's FETs or BJTs or MOSFETs, you have two terminals like a diode. You have a conduction pathway between the two terminals, and then you use a gate to control that pathway. How you use the gate depends on the construction of the device. So in a MOSFET, again, this kind of MOSFET, a channel does not exist. So we use the gate first to create this channel, and then you apply a voltage between the drain and source, which is what we'll see in the next slide. So here is a construction of a N-type MOSFET. N-type MOSFET uses a P-type substrate. Substrate is basically the starting material. It's like your work table. Okay. Here it's also referred to as the body or the bulk of the material, noted by the letter B. Okay. This is the side view right here. And you can see we have a P-type substrate, and we implant N-type regions on the opposite sides of the gate. So there's a gate in the center right here, and we implant N-type materials on either side of the gate. The gate is isolated from the rest of the bulk or the rest of the substrate by the oxide, electrically separate, right? And there's two N-type materials inside the P-type substrate, but there is no pathway, there's no pipe, there's no channel between the two. And right now, theoretically, the device is symmetrical. Yes, Jay. Does it matter where the gate is and the question being asked is about this? The reason for that is, well, actually, there's no overlap. There's the oxide that keeps it separate. Yeah. No, it's important. It's important, and it's right here. Well, actually, we're jumping ahead, but it creates a continuous pathway. Yeah, that's why. Okay. So that's the construction, but you can see N-type material implanted inside P-type material creates a PN junction. Okay, creates a PN junction. So for this reason, the drain and the source must be reverse biased with respect to the bulk of the substrate. So this must be reverse bias. If the drain and source are not reverse bias, then there would be small amount of current that would be flowing through those junctions, and the device will not work properly. So they must be reverse biased to only allow a small leakage current to flow in there across the junction. So that's the first thing. Okay. Now we apply VG. Let's say VG is greater than VTN. Channel establishes, and we can see that next slide right here. So when VGS is far below the threshold voltage, what happens? Device is at equilibrium, so to speak. We have two depletion regions at the drain and the source. Depletion regions at the drain and the source, right? Both are N-type materials implanted in P-type materials. Reverse bias keeps it off. There's a depletion region that exists. When VGS is increased, increase is positive, but it's still below the threshold voltage. You have the negatively charged depletion region that is created. But this depletion region is, again, immobile acceptor atoms, not electrons. Hence the name depletion. Right? If you hear the words or read the words depletion region, you should immediately think there is no free carriers in there to conduct charge. Okay, depleted of charge carriers. So depleted of free charge carriers, still negatively charged. Now VGS crosses threshold voltage, goes positive, and actually charge carriers, and let me see, channel. The word says channel. Okay, channel is established of negative charge carriers, meaning electrons are now attracted because of the positive charge applied at the gate, creates a channel. The channel is now connecting the drain and the source. There's a pipe that is constructed between the drain and the source, and now varying levels of voltage can be applied between the drain and the source. When you apply a voltage between the drain and the source, the electrons can drift or move in response to that externally applied electric field. And because it's moving, we now say current is flowing through the device. Yes. It's a channel of charges. Sorry. But important is just channel. It's a channel of charge carriers, channel created due to charge carriers. And the channel connects both the N-type materials. Okay, both of the N-type materials. And that's why we have an overlap. So AJ, if there was a gap, it would create a small gap. It's a very important observation, actually. There's an overlap. If you didn't have the overlap, let's say something like this. I think time's almost up. We had something like this, and the gate would be here. The channel would be just here, somewhere here. It wouldn't end up connecting both N-type materials. So the overlap is there so that the channel is long enough to connect both N-type materials. Just one more thing. I know we are out of time. So now, again, as I was saying, we can apply a voltage between the drain and the source. And so the electrons can now move in response to that external electric field, hence field effect transistor. Key point here also is a voltage must be applied to create a channel. So this is not a depletion mode device. This is an enhancement mode device. Okay. Enhancement mode device. There are depletion mode MOSFETs. We'll look at those later on. Okay. So we'll end class here today, and I'll see you all on Wednesday.